Hi, I'm Ali Syed, Master of Science in Mechanical Engineering. Now I'm going to discuss a topic about hybrid laminar flow demonstration on aircraft. Before going into depth of this topic, I just want to give a brief description. What is a laminar flow and why it is important in the aircraft industry? So laminar flow is nothing but a proper flow without any disturbance in the flow of the air on the surface of the aircraft. For example, here it's explained using a ball. It's a circular body and there is a flow. If there is no disturbance in the separation of the flow, then this flow is known as a laminar flow. Why it is important on the aircraft, like why it comes into the consideration. For example, here before start, like if there is a wing which is an aerofoil structure, when the air cuts the first tip of the aerofoil, that the same air should flow till the tail of the aerofoil. That should not get separated. If that is separated, the turbulence flow will cause, which will lead to the shock waves in the aeroplane. So the whole process, the whole challenges of the aerospace industry these days is to maintain the laminar flow. There are many advantages of maintaining a laminar flow. Like at the moment, as I'm discussing the challenges of aerospace industry, the very most important one which you're doing at the moment is to reduce the drag. If they reduce the drag, the fuel consumption will be less. With the commercial planes which are in the use at the moment, the whole aerodynamic drag which is coming now because of the design of the aeroplanes will take the 4% of the engine thrust actually, which is a very huge. Even if you decrease the 1% of the aerodynamic drag, and then the fuel consumption saved because of that will be very huge. So now the whole design of the aerospace industry, the whole attributes which are working on that, very most important one is how to reduce the aerodynamic drag or a friction drag. To discuss for that, we'll go into the flow of that. First is the main attributes of the reduced drag. As I explained earlier, why is the laminar flow is really important for that. We'll see what are the main attributes which are causing the drag in the aeroplane. So for example, now the whole thing is described with respect to the nozzle. As here you see the nozzle, when the air flow is cutting from the tip, from the lip section of the nozzle, it goes. If there is a disturbances in the surfaces, if there is any concave or the convex dents on the nozzle, or if there is any improper design or a changes in the structure, will give a spillage drag, which will nothing but causes a shock waves. So what the most important over here is they try to firstly they try to design the whole profile of the nozzle in such a way so that you get the laminar flow. Even when you give a proper design, the most important places where the flow will have a problem is at the off cruise time, which is nothing but at the time of the takeoff or at the low speed levels, or at the top of the climb, which is a cruise time, which is nothing but at the highest peak of the altitude where the aeroplane will experience the highest Mach number and the highest level of mass flow rate. These are the two very most important parts where the flow will get disturbed. So to design with the nozzle actually, so there are the conventional planes which were using before, that was having a certain kind of blunt tip lip section. For example, to explain with what is the differences between the conventional nozzle lip section and what is the difference between the natural laminar flow lip section and what is the difference between the hybrid laminar flow demonstration, which I'm going to explain this. I'll explain it with respect to the lip section of the nozzle. Before going to that, I want to explain what is a natural laminar flow demonstration. So earlier in the 80s and the 70s, the whole aerospace industry was going in such a way that they used to design the whole structure of the nozzle just to reduce as much drag as possible, so that they can have the very profile drag on the nozzle. So later on they started implementing some more complex things. They started implementing some more crucial changes in the design. They tried to make the natural flow which is coming because of the free air stream, to guide it in such a way so that the drag will decrease. So the one is the natural laminar flow. The natural laminar flow was worked crucially in the times of 1980s and the early 90s, but it has its own disadvantages. The main problem it has over here is firstly the conventional lip section of the nozzle. Like I'm just going to draw this tip section of the nozzle over here. So for the conventional, the tip used to be a blunt design, because the whole most idea of this conventional nozzle lip section design was to overcome the suppression flow in the inlet of the nozzle. Whereas in the natural laminar flow nozzle, the tip of the nozzle used to be a sharpened edge, because this sharpened edge was given to overcome the problem the aircraft was facing at the top of the climb. They used to have a proper, they used to have a huge drag. So to reduce the drag, what they have done is they have given a sharpened edge. But this conventional design was failing at the top of the climb, which is at the high altitude, whereas this natural laminar flow nozzle design was failing at the off cruise time, which is nothing but at a takeoff and the lower speeds. So the design what they have given for the hybrid laminar flow is somewhere a compromise design between a conventional design and a natural laminar flow design, which what they have given is they have given a circular design over here, a circular design at the lip section of the nozzle. So this is just a compromise design with respect to the what is the design they required for the reduction of the drag. So this is the first part what they have worked on that. After that, what they have done is they have implemented few things in that. The work what is going on the hybrid laminar flow nozzle is nothing but a continuation, and then extra work which has been implemented and extra research which was done on the natural laminar flow. The reason the natural laminar flow was failing was because it has its own limitations for the mass flow rate, it has its own limitations for the design constraints, and it has its own limitations with respect to the structural design, which was not able to change. Whereas what they have done in the hybrid laminar flow is, it's a whole concept of implementing a bleed suction system of the airspace, which I will go into the depth when I explain about the hybrid laminar flow. So now we'll discuss about what is hybrid laminar flow, what exactly we are going to do in that, and its working. So the whole process of the hybrid laminar flow, what I am going to explain, is taken from the research paper. It's of a United States patent by the Daniel J. and the David. So before going with that, we'll see what is the changes we are doing in the hybrid laminar flow design. This is the nozzle design which you know, and this is the wing, and this is the pylon, and this is the core engine, and the inner core and the outer core. This is a streamline flow which is cutting the nozzle, and this is the intake airflow. The main changes what we are doing over here is we are changing something in the design at the outer surface and the inner surface of the inlet cowl and the fan cowls. We'll see what are the changes we are doing. So the main changes is we are doing over here, because even now the commercial planes what we are seeing, when they go into the top of the climb, most of the planes, as they are having an extreme thrust of the engine, the turbulence flow of the air which is causing the aeroplane shock waves can be controlled because of the thrust and because of the balancing of the aeroplane. But so for that that consumes a lot of fuel consumption. So what they do over here is they're trying to guide the whole flow, airflow, in a proper way of the nozzle. So they're concentrating more on how to change the design and how we can control the whole flow into laminar flow in the inlet cowl and the fan cowl. So the whole process was actually a project actually done by a European Commission, which is a hybrid laminar flow demonstration of the aircraft. They have implemented this hybrid laminar flow on an engine. On engine CFM 56 and 5C engine. Here you can see what are the changes on the design is coming. The maximum diameter of the nozzle will increase because of that. Here in the green, what you can see is the actual nozzle design of the CFM 56 5C engine. The blue end which you see on the top, like the diameter, maximum diameter is increasing. It is increasing because there is a new pump system which has been induced in the hybrid laminar flow nozzle design. We'll see its working and its design over here. Here you can see just a front section, a 4-body design of the nozzle. I'll explain the whole clear process over here, how the hybrid laminar flow is working. The hybrid laminar flow, what they do over here is they suck the air from the boundary layers of the surface of the aeroplane, of the nozzle. Whatever the air is which is cutting the nozzle, they will suck the air from the boundary layers of the surface, and then they use that and then that is taken to the pump, and then that has been exhausted through the fan nozzle. So the reason they are sucking is over here is they are trying to reduce the turbulence flow which is causing on the surfaces of the nozzle. They are trying to guide the whole flow which is coming on the surface of the nozzle to form a proper laminar flow. Here is a sectional view of the whole nozzle design. The red lines what you see over here, that is a duct which is a duct which is taken from the surface of the nozzle and which is guided into the pump. So these ducts are in the series, which can be maintained with respect to its distance, with respect to spaced equation, and based on the pressure distributions. The main the way they calculate the laminar flow, the way they calculate the whole flow of the aeroplane is by demonstrating it with respect to the pressure gradient and also with the coefficient of the dimensionless friction. So to calculate that, before that, what they have done is that changes what they have designed is the whole section is nothing a inlet coal and the fan coal. So within that thickness of the inlet coal, they have designed a ducts. Over here is the outer surface of the nozzle and this is the inner surface of the nozzle. And the outer surface of the nozzle, you can see the red lines which is coming through, that is the ducts, and the inner nozzle as well, you have the ducts which will be cutting through. So all the ducts which are on the outer surface will be connected, will be joined at the end, and the whole air which is taking will be coming to the single pump wall. So there are two walls in this whole section. One wall is for the air which is sucked from the outer surface, another wall is for the air which is sucked from the internal surface. I'll explain why there are two walls, what is its importance over here. So from the wall it is taken to the pump, and pump will exhaust the whole air with an extra pressure from the fan nozzle. So as I explained, the problems, the hybrid laminar flow project is nothing but the overstudy, the research what has been continued and they studied on the natural laminar flow. The main two problems the natural laminar flow nozzle was facing was a suppression flow at the low speeds and the off cruise time, and a higher price like a shock waves and the spillage drag and the higher drag in the top of the climb at the cruise time. So these two, by keeping as the main problems over here, they have induced the internal duct and the outer duct. Now how it works actually. So if in the lower speed or at the takeoff time, what they do is they will close the walls which will do the suction of the air from the outer surface. Only the internal duct will be open. So internal duct is open, so this can control the suppression flow in the inlet of the air. So what happens is, if the flight is going with a certain speed at a certain Mach number, the mass flow rate, the exposure of the air to the nozzle will be more. But at the lower speeds, at the Mach number of the air will be less. The fan will not get enough mass flow rate. It has to be in a proper laminar flow to get the actual mass flow rate. If there is a turbulence of the air in the lower speed, then the fan will not get the enough mass flow rate. So for that reason, what they do is they just open the internal duct over here. So only this wall will be open. So this will suck the air over here, and the suppression flow can be eliminated by this process. Whereas in the top of the climb, at the cruise time, at the highest point where the aeroplane will face the maximum Mach number and the maximum mass flow rate, at that time what they do is they will close this wall. It means the suction of the air will stop in the internal. Only the outer surface will be open. The outer surface will be open because the whole air what is cutting the outer surface of the air can be controlled by suction of the air over here. So the whole process will give the profile or a laminar flow. So this profile will reduce the drag, which will directly increase the efficiency. So this is the working actually. As you can see, I will just give a brief line diagram once again. This is the outer ducts from the outer surface, and this is the inner duct from the inner surface. Inner surface ducts will be connected to a separate wall, and the outer surface ducts will be connected to the outer wall, and these two walls are combinedly connected to the pump. So as per the requirement, at the off cruise time, the wall which is for the inlet ducts will be open, and at the top of the climb cruise, at the maximum cruise time, the outer surface ducts will be open. So using that, they control the laminar flow, and the two major problems which the industry was facing because of the on the natural laminar flow nozzle can be eliminated using this process. So as I explained, this has been totally taken from the hybrid laminar flow nozzle. It's a US patent done by Daniel J, David E. Yates, Ping Mover and Envo Stockman. They have been done by assigning the whole project by the GE company in the Ohio, and the whole thing was actually done to overcome the problems the natural laminar flow nozzle was facing. So far we have discussed the hybrid laminar flow. So at the end, I want to give what is the differences, what is the changes like they have seen in the flow in terms of pressure gradient and in terms of Mach number for the conventional nozzle, for the natural laminar flow nozzle and the hybrid laminar flow nozzle. So pressure gradient, as I explained, the whole flow can be measured
by putting the sensors on the edge of the outer surface of the plane, and they measure what is the pressure distribution at each and every point of the nozzle. For the laminar flow, the pressure gradients at each and every point of the surface should be equal. Only then a laminar flow can be there. Even if there is a maximum difference between the pressure, there is a chances of having a turbulent flow, which will again leads to the shock waves. So here you can see the conventional nozzle. The red line, what you see is the graph of the Mach number with respect to the surface and the speed. The green one is nothing but a pressure gradient. Over here, this is for the conventional. As you can see, there is not a proper uniform line for the Mach number. There is a disturbances of the Mach number. And also you can see the pressure gradient is also not in a proper way. That is, there are maximum and the ups and downs of the pressure gradients of the whole surface of the nozzle. Whereas in the natural laminar flow, to the some point, and for the Mach number you can say, to the some point, for the top of the climb, till the plane reaches to the top of the climb, there is a laminar flow. There is the transition from the laminar to the turbulent can be delayed till the top of the climb. But when it goes to the top of the cruise, there is a reduction in the Mach number, because that is where you will have the shock waves because of the spillage track. Similarly, even the pressure gradients that will decrease initially, and later on that will increase because of the spillage track. Whereas over here, if you see the hybrid laminar flow nozzle, from starting you can see there is a continuity in the Mach number, there is a continuity in the pressure gradient, and then that will be decreased later on. So the whole flow can be maintained to some point. Even when the flight is landing, the whole Mach number will be decreased, but still that can be maintained to the level. So this is the actual difference what they have calculated from the conventional nozzle, natural laminar flow, and the hybrid laminar flow. So this is the actual work which was done by the hybrid laminar flow by the scientists. So this whole concept was invented by these people, and they have patented it. So this work was taken further, and all the aerospace companies, what they have done is they have conducted a project using this hybrid laminar flow concept, and they tested live on a aircraft which is A340, and the engine used in this was CFM56-5C. This whole project was actually sponsored by the European Commission, and it also has all the 11 to 15 of the companies supporting that, including Boeing, GE, Airbus, and European Wind Tunnel Association. So all the companies came together. In 1996, they have started a project which is HYLDA project, like Hybrid Laminar Flow Demonstration of the Aircraft project. They used this concept in that aeroplane, and the whole project duration was for 42 months. And after doing continuous projects and changing the concepts, like so far the concept what I have explained was of 1991. In 1996, by the time they came, they have done some more extra work on that, on the materials, on the structure, on the design. And for the materials, they made it with the composite materials so that they can reduce the weight. And for the structures, they have gone for the very compact design so that they can have the proper laminar flow on the nozzle. So after doing all that project, what is the conclusion they got? The conclusion is like they were able to maintain the laminar flow till the 50% of the chord. I'll tell you what is the result they have gained because of achieving a laminar flow for the 50% of the chord. And after that, they have done a more laboratory work for the lightweight materials, which also will, as there will be a decrease in the weight, they will have the benefit of efficiency. And a database for system design, they were able to cover the whole database of the pressure gradients and also the Mach number at the inlet, outlet, and also at the end of the nozzle. So the whole thing what they achieved is they were able to reduce the whole drag of the aeroplane by 35% because of this hybrid laminar flow nozzle design. So this is a very huge thing. 35% of drag reduction is nothing but it's a huge drop in the fuel consumption of the aeroplane. The whole thrust which you are getting because of the engine can be consumed more if the drag is less. So that is what finally they achieved. What is the problems they were facing in the project was the risks what they are having is because due to the structure, because if there is even a design or even if there is a problems in the manufacturing of the whole nozzle problems, and there will be a turbulent flow, there will be a suppression flow. So even the manufacture has to be done really carefully, and even the material that has to be very light, and the maintainability in the nozzle is a really big thing over here, because this whole hybrid laminar flow nozzle structure will have a pumps and ducts and extra all the accessories inside that. So it's really tough for a aircraft maintenance to maintain the whole nozzle and its engine. Apart from that, it has to maintain the hybrid laminar flow as well. So these are the few of the risks which was going on. And the future works over here is using more electric components. As there is a high weight and everything, they're trying to reduce everything by using some electric components, and they're trying to refine this research, and they're trying to make it very compact design and optimum. And by eliminating the fan accessories, and they can implement the whole hybrid laminar flow system over there. So that will result in the more lighter, reliable, and the efficient design of the whole hybrid laminar flow design, hybrid laminar flow nozzle. So this is the project what they have done by European Commission and the list of the companies including that. So this will give a brief idea about what is the latest work which is going on the nozzle, which is hybrid laminar flow, and what is the work of aerospace industry has done in 1996 using hybrid laminar flow demonstration of the aircraft project. Thank you.